Right now, somewhere past Neptune, something is pulling on our solar system, about 5 times the mass of the Earth. We've tracked its gravity for years, and we have never once seen it. In 2020, 2 physicists offered an answer stranger than any missing planet. What if it isn't a planet at all? What if our solar system has been hiding a black hole, one small enough to hold in your hand? A black hole with the mass of 5 Earths would be about 9 centimeters across, the size of a tennis ball. It could be out there in the dark right now, almost perfectly invisible. So which is it? A hidden planet or a hole in space the size of your fist? We still don't know. To see why anyone takes this seriously, start with what's actually out there. The story begins in 2016 in a paper by Konstantin Batygin and Mike Brown at Caltech. They had been tracking a population of objects in the outer solar system called extreme trans-Neptunian objects, frozen rocks and ice bodies orbiting at distances of 300 astronomical units or more, where 1 astronomical unit is the distance from the Earth to the Sun.
These objects were not moving randomly. Their orbits were clustered. They all leaned the same direction. They all had perihelion, the closest point to the Sun, at roughly the same place in space. Statistically, that does not happen by accident. The Kuiper Belt is supposed to be a chaotic graveyard, bodies left over from the formation of the solar system, scattered by interactions with Neptune over billions of years. There is no known mechanism that would naturally align their orbits this way. Something has to be doing it. The specific objects that triggered the analysis include Sedna, discovered in 2003, with an orbit so distant and so eccentric that its existence was already a puzzle on its own. 2012 VP113, 2007 TG422. Together they form a small but consistent population, and the gravitational source needed to herd them into the pattern they show is large, Earth mass or larger. Batygin and Brown calculated that the simplest explanation was a single unseen body, somewhere between 5 and 10 Earth masses, in an extremely elongated orbit, 400 to 800 astronomical units from the Sun, with a period of roughly 20,000 years. They called it Planet 9. The hypothesis was clean. The math worked. The orbital architecture fit. The only thing missing was the planet. In the 9 years since, every major survey capable of looking at the outer solar system has looked. The Subaru telescope, Pan-STARRS, the Dark Energy Survey. The Vera Rubin Observatory, just coming online, will be the most thorough yet. So far, no candidate has been confirmed. If Planet 9 exists and is made of rock and ice, it should reflect a small but measurable amount of sunlight. The problem is the inverse square law. At 700 astronomical units, that reflected light is roughly 500,000 times fainter than what an equivalent object would return from Neptune's orbit. It is faint, but it is not impossible to detect with modern surveys. We have looked. We have not found it. But a hidden planet was the boring answer. The idea 2 physicists put forward in 2020 was stranger and a lot more disturbing.
In 1971, Stephen Hawking proposed that during the first fraction of a second of the universe, when matter and energy were compressed at densities no star has ever reached, some regions could have collapsed directly into black holes. Not from dying stars, from the raw chaos of the Big Bang itself. These objects are called primordial black holes. A primordial black hole does not need to be massive. The Big Bang produced fluctuations on every possible scale.
The smallest theoretical PBHs would have evaporated almost immediately through Hawking radiation. But anything with a mass above roughly 10 to the 11 kilograms, about 100,000 tons, would have survived to the present day. And here is where the geometry gets strange. The radius of a black hole, its event horizon, is determined by its mass through one equation, called the Schwarzschild radius. For an object of 5 Earth masses, that radius is roughly 9 centimeters. 9 centimeters. A black hole with the mass of 5 planets would be the size of a tennis ball. It would have no surface. It would emit no light. It would reflect no light. It would be perfectly black against the perfect black of deep space. The only signal it would produce is gravity.
In 2020, 2 physicists at the University of Illinois, Jakub Scholtz and James Unwin, published a paper that took this seriously. They asked a direct question: could Planet 9 be a primordial black hole? Their conclusion was that the gravitational signature would be identical. A point mass of 5 to 10 Earth masses at 400 to 800 astronomical units would perturb the Kuiper Belt the same way whether it was a planet or a black hole. The orbits would not be able to tell the difference. But the searches would. A PBH would not reflect sunlight. It would not appear in any optical or infrared survey. It would only show up if you saw something else. A distant star, a comet, passing close enough to be gravitationally lensed by it. And there is one more constraint that makes the idea uncomfortable. Primordial black holes have been proposed as a candidate for dark matter. Observational limits from microlensing surveys like Ogle and Subaru HSC have narrowed which mass ranges could host significant dark matter contributions. The Earth mass range is in one of the remaining unconstrained windows. The hypothesis is still alive, and it raises a question almost nobody likes to ask out loud. What would one of these actually do if it ever came close? The Planet 9 PBH, if it exists, is stable in its orbit. It is not coming for Earth. But the question of what a primordial black hole would do if it ever did get close is one of the more uncomfortable thought experiments in modern physics. A PBH with the mass of a small asteroid, millions of tons, but only the size of an atom, would behave differently from anything we have ever modeled. It would not crater the Earth on impact. There is no impact in the classical sense. The cross-section of the event horizon is too small. What it would do is pass through. A 9-centimeter event horizon moving at solar system escape velocity would punch a narrow tunnel through the planet, accreting material along its path in a process called dynamical friction. The energy released would be enormous. Most of it would be deposited along the tunnel itself, a column of intensely heated, fractured rock running from one side of the Earth to the other. What this would look like at the surface depends entirely on size and speed. Small PBHs would produce localized seismic events. A larger one, closer to Planet 9 masses, would deposit enough energy to deform the planet's mantle, trigger global earthquakes, and superheat its passage tunnel to the point of triggering long-duration volcanic activity along the entry and exit zones. The atmosphere would not boil away from a single passage, but the geological consequences would unfold for centuries. There is one historical proposal that takes this farther. In a 1973 paper, Albert Jackson and Michael Ryan suggested that the 1908 Tunguska event in Siberia, a 12-megaton explosion over uninhabited forest, the largest atmospheric impact event in recorded history, could have been caused by a small primordial black hole passing through the Earth.
The hypothesis required an exit signature on the opposite side of the planet that was never found. It was abandoned. But it sits in the literature as the first time anyone seriously asked the question.
The modern version of the question is more careful. PBHs in the asteroid mass range, if they exist in cosmologically interesting numbers, would interact with the Earth on geological timescales. Surveys of seismic data for unexplained singular events have been proposed, but never produced a hit. The absence is itself a constraint on the population density. None of this is happening. Planet 9, if it exists, is on a stable, wide orbit. There is no PBH headed for Earth. The closest detection programs are looking at much smaller PBHs in the asteroid mass range, where the predicted population is highest and the cosmological constraints tightest. But the architecture of the solar system has a gap in it. Something with the gravity of several Earths is shaping the orbits of the outer Kuiper Belt. 9 years of dedicated surveys have not produced a reflective object. And the most boring explanation, that it is a planet too dark or too distant to find, is no longer the only one on the table.
The next decade of observation, especially with Vera Rubin, will resolve this one way or the other. Either we find a faint, cold body where the math says it should be, and Planet 9 becomes the 8th planet, again. Or we keep not finding it. And the more elegant explanation, the one that fits the data without inventing a new world, starts looking more like the answer. So look again at that dark patch past Neptune. Something 5 times the mass of the Earth is bending the orbits out there, and it might be small enough to hold in your hand. A planet too faint to see, or a relic from the first second of the universe, caught in orbit around our sun. We felt it pulling for years. We still can't say which one it is.